All right, we are recording. Let's go from current slide. Okay. Now, a couple things before we get started. I've done this several times already, and I'll keep doing it until the bitter end now, I guess. Okay, first and foremost, let me tell you about a few changes to office hours. Well, let's start with the course first. We should finish chapter 24 today, which means we should have time to do the lab today. And then the last 30 minutes today will be the test on chapter 23. Okay? Hope you got your formulas and equation sheets ready for that. So, and I was saying before, but a couple more people have come in, or one more anyway. I haven't heard back from Channel 13, or at least I haven't found it anywhere. They could have emailed me this morning. Didn't have a chance to look over lunch. As soon as I know something, I'll try to let you know. But I guess it's a safe assumption we're probably not going today. Okay. I'm hoping we can go on Tuesday. Okay. If not, I hope we can go on Thursday. Okay. If not, we run out of time. So, unless we know something else, we'll just plan for that. Now, what will we do if we don't? Well, okay. Let me start over. Before I get negative on it, let's go here. I want to review this with you quickly. So far, 5 people out of 15 have turned in their papers. This is the last weekend you got before the term's over, folks. So please try to get your papers completed and get to me by Tuesday, because Thursday is final exam day. I want those papers in by Tuesday. Okay? Was there a question or just scratching? Okay. All right. So please get the papers in. Now that's going to come back possibly and haunt you, so hold on that. Lab 1, still 2 people haven't turned in Lab 1. Okay? Test 1, everyone's turned in. I returned those to you on last time. Is anyone here who did not get their Test 1? Okay. Lab 2, all but 2 people have turned in Lab 2. Test 2, everybody turned that in. Is anyone here that did not get Test 2? Okay. Lab 3, uno person has turned in Lab 3. That's the Moon Lab. The Moon's basically just about not in sight much anymore, so hopefully you've gotten all your observations. Get the lab in as soon as you can. Okay? Only 1 person has so far. Test 3, I returned quite a while ago. Is anyone here who didn't get Test 3 back? Okay, Lab 4. 1, 2, 3, 4, 5 people haven't turned in. Oh, no, I'm sorry. Lab 4 was the visit to the planetarium. If you were there, you got your 25. If you weren't, you didn't. Okay? Lab 5. 1, 2 people haven't turned in Lab 5. Test 4. 1, 2, 3 people hadn't done Test 4. 1 turned it in today, so still 2 people haven't done Test 4. Lab 6. 1, 2, 3, 4, 5, 6. 6 people haven't turned in Lab 6. Yeah. That was the one with the questions, 15 questions. Okay? Turn in at least what we did in class, okay? Test 5. 1, 2, 3. 3 people haven't. 3 haven't. I got 1 today, okay? Done Test 5. Lab 7. 1, 2 people haven't done Lab 7, haven't turned it in anyway. Test 6. 1, 2, 3, 4, 5, 6, 7. Now that was a take-home test, right? Now 1 turned it in today. Ought to have those in, folks. Lab 8, 1, 2, 3 people haven't turned in Lab 8. And Test 7, we had last time. I haven't finished grading those, but I'll probably finish grading those while y'all are working on labs and tests today. Okay, now why did I go through all that yet again? Here's why. I want to return everything to you on Tuesday. Now, I don't know if and when we're going to the Channel 13. If it's early in the day, then we'll just head out, and then we'll come back here. And when we get back here, I'll return everything to you. If we go there sort of middle of the period, kinda, I'll turn them all back to you early in the period, and then we'll leave and go to Channel 13. Same thing if we go late, but I don't think we'll be going late because I think Jerry Tracy, gets busy right near weather time. So I think the best time is like 2 to 3 o'clock in the afternoon, something like that. So that's why I figure it might be middle of the day-ish, middle of the period. All right, so I will be returning everything to you on Tuesday. Okay. Then on Thursday, all that's left is the final exam. Okay. Now, we'll have plenty of time for if you need to catch up things or make up things, unless, of course, the field trip gets moved to Thursday, and then you still have plenty of time. It won't take more than an hour or two there, maybe an hour and a half to get there and back. We still got plenty of time, so won't be a problem with the final exam. Okay. Here is what I consider sort of worst case scenario. What if we don't get to go on the field trip? What if they say, no, we're just too busy, or we're not going to be here, or we got an inspection going, something that we can't have the field trip? What are we going to do Tuesday if we don't go on the field trip Tuesday? Here's what my suggestion would be. Now, you won't like the way it starts off. Another lab opportunity. Okay? Except this lab opportunity will be you're presenting your work on your paper. Okay? So if we don't get to go to the Channel 13 on Tuesday, that's what we'll be doing. Okay? On Tuesday is you'll be presenting. And if you present, you'll get another 25 points. If you don't present, you won't. Okay? So, number one, that means you got to get your papers done. Okay? And number two, be ready to present your papers and do it. You can use PowerPoints if you want to. It's not absolutely required, but you do need to tell the rest of the class about your paper. Okay? Now, if we get to go to Channel 13, most of the day will be spent returning stuff to you, going on the field trip. And then what we'll do when we come back here, if any of you are behind in a lab or a test, that will be a makeup day, okay, to catch up anything you may be missing. And as soon as you turn it in, I'll try to get it graded and back to you. What's that? Y'all are not going on the field trip today. I don't think so. I called them Tuesday, I called them yesterday, I called them twice today. And I did get to talk with someone Tuesday, and she said she'd email me that afternoon. I haven't seen the email yet, okay? So I don't know what happened then. And I called Jerry Tracy yesterday because I had an opportunity to, and I thought he was in. I went to his voicemail. Haven't heard back. And then today I tried Harmony Mendoza twice, and they sent me the voicemail both times. I left a message the first time. I didn't bother with it the second time. So I don't think we'll be going today. I don't have a vehicle. I don't have any of that. But I do have Shelby here. Okay. All right. Now, I went through a big spiel for those people who've just come in. You're going to have to listen to YouTube to find out what that spiel was. Okay. Any other questions? The odds are I'm hoping the field trip will be on Tuesday. And if it's not, we'll be presenting papers on Tuesdays. Okay? Number one, you got to have your papers in. Number two, now, if any of you need your papers back to work up the 5 people that have turned it in, I can return those to you, but they have to come back to me next week. Have to. So if any of you need the papers, I can return them to you while you prepare your presentations. I forgot this part. This is where I started off. One confounding issue here is normally on Fridays I'm on the Birmingham campus 7:45 to 1. Usually later than 1, but at least 7:45 to 1. Tomorrow I'm in Opelika. Okay, we've got math meetings going on, and we'll be leaving the Birmingham campus at 6 in the morning and coming back around 6 in the evening. So I will not be on campus anytime that I can make phone calls or send emails or put announcements on Blackboard or anything else. I'm going to be in Opelika at meetings all day tomorrow. Now let me cover this too, not that it really, I don't think will bother any of you. Next Friday, I won't be on Birmingham campus in the morning either. I've got my annual physical next Friday at 8 o'clock in the morning, so I'll be at the Clarkson Clinic from 7:45 until the physical's over. I'm hoping it'll be through by 9, and if it is, then I'll try to get back to Birmingham campus by 9:45 or 10 o'clock, something like that. So I hope to be there the latter part of my Friday, but I won't be there the first part. All right, any questions on anything before we get started today? Okay. All right. Now, before we get started, I think I mentioned this last time, on page 612 or somewhere thereabouts in your text, there is a very good little blurb. It's almost half a page on estuary pollution. Does anyone know what we mean by an estuary? It's basically the collection of water in a low-lying area, usually right before it dumps into the bay, the ocean, the sea, or whatever it's going to. It's where the waters begin to mix. The brackish salt water and the fresh water, those are usually your estuaries, okay? Now, that may not always fit exactly, but those are extremely important features, well worth a read. Closer look, top of page 612 or somewhere there. Okay, after that, let's look at movement of seawater. Remember, the progression of the chapter, we started with fresh water. I can't remember the exact order. I think groundwater, surface water, maybe surface water, then groundwater, and then we got into seawater. Got a little wet. Okay. So we're moving on and talking about the movement of seawater. We talked about the oceans, the seas, and all the things that make up seawater. Let's talk about how it moves. The mixing time of Earth's seawater, I forget it every time. I'll be right back. Okay, how much of the Earth's surface is covered with seawater? Yeah, about 70%. 2/3 is not far off. About 70%. Is it 73? Say again? Isn't it 73? It's close to that. Different slides have said different things. Around 70%, 68, 73, somewhere in that range. Covered with the oceans. Okay? That's a lot of water. A whole lot of water. So what's the mixing time for all that seawater? It goes from the North Pole, South Pole, all the way around. Okay? All over the place. We get a complete mixing of all the oceans, all the seawater, every 2,000 years. 2 millennia. We have a complete mixing. Okay? But it's always going on. So what does that mean? we've had about 1.5 million mixes over the 3 billion years we think we've been in existence as we consider ourselves. Now, two types of motions. The wave motions are pretty much surface disturbance. They can go a little below the surface, but they're mostly surface disturbances. Largely caused by winds, but can be caused by other features like earthquakes and things like that. That's pretty much a surface phenomenon. That mixes things up on or near the surface. The second of these types of motions are currents. This is movement of water from one place to another, and these can be deep currents or shallow currents or something, and we've already mentioned one of those. Remember one we mentioned last time? It begins around the Gulf of Mexico. Current, the Gulf Stream. It keeps most of the U.S. ports free of ice all winter long because that warm water comes up the east coast of the U.S. Unfortunately, Canada doesn't get so lucky because you have a cold stream that comes down and freezes most of theirs, but most of ours are good, and actually crosses the Atlantic. And also those warm waters from the Gulf Stream, fantastic areas for fish to live and to thrive. At least in the past it was. We've almost fished out the Gulf Stream. I mean, it was just amazing fishing, and everybody in the world started fishing there, and now the fish aren't in nearly the abundance they used to be. But that comes on across and actually keeps Ireland and Great Britain from freezing most of the winter too. So it benefits lots of places here. Scandinavia freezes like crazy. It doesn't reach that far. It bends south and goes from there. Okay, that's one current. There are many, many, many other currents. So this is movement of water from one place to another in a pretty steady, consistent manner. Okay? So let's look at the first of those, waves. Waves are the simplest structure we've got doing. They're moving crests and troughs. You've all seen waves before. If no place else, a bathtub when you're a kid, playing around, getting the water moving. Now, three characteristics of the waves. First of these is the wave height. Okay? And the wave height is the distance from the crest to the trough. Every wave is made up of basically those two parts. You have a peak somewhere here, and you have a valley. The valley is called the trough. So the distance, vertical distance from the crest to the top of the crest to the bottom of the trough, that's called the wave height. Vertical distance from trough to crest. Then we have a wavelength, and by the way, that's the distance measured in feet or meters or inches or yards or whatever. Okay. Then we have a wavelength, also measured in distance. The horizontal distance between two consecutive crests or two consecutive troughs is just harder to measure where the bottom of a trough is. Usually a lot easier to measure the top of a crest. That's called the wavelength, also measured in a distance measurement. And then the third is not a distance. The third is a time, the wave period. It's the time that passes between two consecutive crests. Okay, now these waves aren't just standing there. They're not standing waves. Waves are always moving. So what you do, you measure crest to crest, that's a wavelength. What you do is fix a point here, start a stopwatch when this crest moves off, and then the next crest reaches you, stop it, and that's your wavelength. The wave period. The time between the passage of two consecutive crests by the same point. So you need to sort of have something fixed in space so you can measure the time it takes one crest to get from one crest to another. So those are the major characteristics of a wave. Now, most of the ocean waves are from the wind. Occasionally there are waves that don't come from the wind, but most of them are from the wind. The characteristics depend on three factors. Okay? Number one, how fast is the wind blowing? Okay? Certainly, the stronger the wind, the faster it's blowing, typically the taller waves you'll get, greater wave height. Typically, you're going to get longer wave lengths, and that may actually decrease the wave period because the waves may be moving faster. So the wind speed is certainly one factor that influences those three characteristics. Okay? Now, wind speed is one. The other, though, and this is actually perhaps more important, the length of time that the wind has been blowing at or near that speed and from that direction. Okay? Now, why is this important? Have any of you had to ever push off a car or a truck or vehicle or something? Okay? How did that go about? You just get there and push as hard as you can? Not usually.
No, usually you gotta get something under the wheel and then push.
Okay? Certainly that, but once you're pushing, you don't just brute force it most of the time. What you do is sort of get it rocking, right? Okay? You push. It's sort of like pushing a kid in the swing, or an adult in the swing too. You don't push right when they come up. You let it reach its peak, and then you push again, and they go higher. Let it reach its peak, and push again, and they go higher until they start screaming or you get to be dangerous or something. Well, that's what's happening the longer the wind blows from the same direction. What you do is build up the waves. In fact, beyond the waves, they talk about swells. I think they'll finally get to that over here, but generally, the longer the wind has been blowing at or near that constant speed from the same direction, then the longer you're building up the waves. We call that practice resonance, okay? When you push on the swing or push on a car or the wind blowing in the same direction, you start reinforcing the cycle of that. And as you do that, you build wave height, could extend the wavelength, and depends on the speed of it, you know, the period, wave period as well. The third of these factors that influence those characteristics is what they call fetch. That's not what your dog does for you, okay? That is fetching, but this is a different kind. That's the distance the wind blows across the open ocean. Okay? Now, as you might guess, the Pacific should have quite a long fetch. Okay? Because it's a big ocean. But really, all the oceans they are big. And it's the distance that the wind blows across that open ocean without any impediment. In other words, without changing direction and without doing anything else. That's fetch. And the longer the fetch, now, usually the taller the waves, perhaps the longer the wavelength, period, it depends on pretty much on speed. Okay? When I lived in Nebraska, I did graduate work in Nebraska, the wind was brutal up there, especially in the wintertime, because there was nothing but wide open prairie. So you said that wind came straight down from Canada and didn't have anything to get in its way. So it built speed, it built intensity, and everything else. Same thing about the open ocean. The greater the distance that wind is blown across that open ocean in the same direction at nearly the same speed, then the greater you're building those characteristics. So those three factors: how fast the wind is blowing, the length of time it's been blowing at that speed or near that speed, and the distance over which it's been blowing for that speed. Now, in reality, quite often the wind changes pretty rapidly, okay? Not super rapidly, but it can change fairly rapidly. So we wind up with a complex mixture of wavelengths and wave heights being generated, okay? Say the wind speed has changed a lot. The wind direction's changed a lot. The length of time over which it was blowing from a given direction at a given speed has been varying like crazy. And maybe even the fetch. Maybe a few islands got in the way or other things. So other things could be good. So it can be a really complicated mixture of wavelengths and heights generated. Generally, the smaller waves dissipate from friction within the water. Now that sounds a little bizarre, but water has friction too. You know that, don't you? If you've ever been in the water, you push against the water and that helps you swim, right? The water has friction. It's resisting your motion. It's resisting the motion of your hand, and that's what helps propel you forward. Okay? So, smaller waves tend to die off. Okay? The larger waves, however, last longer, typically travel faster, meaning the wave periods would be less, and eventually coalesce into a swell. And that's what I was getting at, was the swell. If you've had wind blowing again across the ocean at a fairly rapid speed for a long period of time in the same direction for a very long distance, not only are you building up waves, you're building up swells. Now swells, and when I was in the Navy, we used to note these things. The swells could be coming from one direction, the waves from a slightly different direction. Why? Because the wind had changed and created waves here, but it had been a long time blowing from this way, so the swells were still coming in from this side. Okay? Most of the time they're not far off, but quite often they are off somewhat. Usually those are smaller waves if they're way off from what the swells are. Okay, so that's what swells are. Long period waves that are built up over time. So let's look at swells. They carry energy but do not transport much water. Waves, the water gets pushed along back and forth, moved around, mixed around. The swells, the water basically goes up and down. The swells move like this, the energy transfers like this, but actually the water actually goes up and down. Any of you ever fished with a bobber? Okay? If you have, you know it might be lots of swells and stuff there, but the bobber basically goes up and down. It doesn't drift off down. If you have a current, it can pull it off. But most of the time, waves come by, the bobber just goes up and down. Okay? That's what we're talking about here. The swells carry energy, but actually don't transport a lot of water. The individual particle motions are circular, and the diameter is the wave height. And this next slide shows it somewhat. I'm not sure this is a pretty good slide. One of the ones coming up later isn't quite as good. But, again, remembering, distance from trough to crest, that's the wave height. Distance between crest, wave length, and the time between crest, wave period. Okay? Now, if this is indeed a swell rather than a wave, the particles, if you picture this, the lowest that surface particle can go is here, the highest it's going to go is there. So basically the particle travels somewhat in a circle. Let's say start it here, and the wave is moving here, it goes down, up, and down, it basically follows a pattern like this. There's not much transport of water. The water goes up and down. The swell moves left to right or whichever reason it's moving. Okay? So there's motion like that. The diameter near the surface is the wave height. Now, a few other terms. Whitecaps can either be on waves or swells, more likely swells, but occasionally waves. They're formed when the top of the swell is toppled by a strong wind. If this wave is getting taller and taller and you've got a fair amount of wind coming behind it, you know, that's a lot of water sitting up here without much support. The wind, if it's strong enough, blows it over, and that makes what they call the white tops. Now that will do a little more mixing than just the regular old swells, but not a lot more. Now, what this slide is showing in the verbiage is not keeping up with it. The mixing goes on mostly at the surface. And as I said before, waves and swells are mostly a surface phenomenon. Mostly a surface phenomenon without a lot of mixing otherwise. So this up here, this gets pretty messed up, you know, and especially if you have white caps, it's really rugged here. You go down a little way and the diameter decreases. You still have circular motion of particles here, but not much. When you get another half a wavelength down, okay, now, here's the part that's a little confusing. That's a wavelength, but if you go one wavelength down from the center part of that wave, half a wavelength down, you have a little bit of mixing, one wavelength down, no motion below the depth of one half of a wavelength. Now, this is part of the slide that's a little confusing. They show this as one half of a wavelength, but then they show this as no motion. But if you had extended this down to there, you're going to be pretty close to there. So I think it's one half of a wavelength, which is this one, a horizontal length, down from your trough. Below that, you hardly have any motion at all. Not from waves or swells. No surface mixing to speak of. So you see all your surface mixing is one wavelength. Now, if these are long wavelengths, you have more mixing. Short wavelengths, not very much mixing at all. It's all right at the surface. Does that kind of make sense? Okay. Now, most of the time, most of us, our greatest experience with the ocean has probably been on the beach, okay, on the beaches. And here we have shore effect. When you see waves on the beach, they look different from waves or swells out in the middle of the ocean. They're still the same characteristics, but the shore effects have enhanced the appearance of those waves. And we're going to talk about several of those, features of those. The first is called refraction. Now that's a very physics or physical sounding word, and indeed it is. And this doesn't show it. Okay, sorry about this. Let me see if there's a later slide that does. A little bit there, but not so much. A little bit there. No. Okay. Let's picture a beach. Let's say the beach is this line right across here. Well, let's say the waves are coming in this way, not straight on into the beach. If they were, they'd just crash into the beach. But let's say they're coming in this way. Now, the shoreward side of the wave slows down because of friction with the soil over here, with the beach itself. The other part speeds up. So it makes it look like the wave is bending. And that's called the refraction. The shoreward side of the wave slows, the wave front bends toward the shore. Okay? It tends to bend toward the shore. You see a little bit of it, not much. In a couple of the next slides, just a little bit. This one shows almost the wave coming straight in, not quite, okay? Certainly the beach is here, it's kind of on that line, and the wave is like this, and it seems to be getting a little bit closer down here than it is here, so it is bending toward the shore, okay? That's what happens. Now, back up here, let's talk about breakers. at depths less than 1 wavelength. Now remember, the wavelength is the distance crest to crest, but now we're doing depth of a wavelength down like this. So at depths less than the back off. They're showing wavelength there, they're talking about wave height here. This is what's confusing about these slides. At depths less than 1 wave height. Now wave height is crest to trough, okay? They really don't show it well here, but that would be about 1 wave height. At depths less than that wave height, the lower part slows and the top part breaks forward. That's why we call it a breaker. So you see, if this is 1 wave height here, as long as the bottom, the sea bottom, doesn't interfere with that, it travels just like it did way out there in the ocean. But when you get up near the shore, where you're less than 1 wave height, okay, the lower part slows, and there's 2 reasons for that. One is friction with the sea bottom, okay? You have more friction there, so that's going to slow it down. But the second feature is the water from the previous wave is having to come back down now. That slows it down. So both of these actions then get your bottom dragging, your top going along at the regular speed, and now you get a breaker there. Now that breaker isn't caused by the wind. That breaker is caused by the lower part slowing, the top part breaking over the top of it. Now, that's what the surfers like to call the surf, the breaker formation zone, where you get these. And of course, the taller the wave here, the more the surfers like it. Anyone know what some of the premier surfing sites on the globe are? Hawaii, absolutely. If not just Hawaii, get it in here somewhere. Here we go. Okay. Hawaiian Islands here. They're usually, you'll hear them talk about the North Shore. Okay, and if you think about what we talked about, look west of Hawaii. Pretty much nothing but water. Okay, you're in the prevailing. Hawaii is, part of it is in the tropics and part of it is just above the tropics. So you're right at that borderline. And I assume that most of the, well, let me put it this way. Nothing to the east or west, and wherever the waves are coming from, they're coming over long periods, lots of fetch, lots of good steady wind. Those waves and swells build and build, and then they hit the islands, and they break big, really, really big, okay? So that's the breaker formation zone, when you're less than 1 wave height above the bottom, then you get the breaking action. Now, water transported toward the shore must return. That's what I was talking about before. You have the 2 things going on, friction with the sea bottom, okay, but also returning water from the previous waves. Both of those tend to slow down the under part and make the breakers break bigger, okay, or taller, okay? Now, that water being transported back is called your undertow. And if there's anything that's dangerous about the beach, this is probably the main thing. You get these undertow that can actually drag you under, okay? Water's coming at you this way, pulling that way. It can topple you in the water and sometimes be a very scary experience. Direct return of the water underneath the breakers. Now, another feature of that, water being transported toward the shore by breakers, longshore currents, okay? I think this next slide will show this a little bit better. Now, back up here, this is an actual picture, not an illustration. And you can see, if you use your imagination, there's a crest, probably a crest there. These are your swells coming in. Here's one here, here's one there. They're coming in at fairly regular wavelengths, okay? But when they hit near the shore here, you see all the white cap action, and that's because the shore that's underneath the water here is resisting the motion. The water on top is not resisting motion, so that's why you have the breakers happening near the shore. Now, I can't tell you exactly what's happening while they're not happening here and here as much as they are there and there. I have a feeling it has to do with the contour of the bottom. Most of the time that's the situation there. Maybe it's a little bit deeper there so you don't have the resistance. Okay. Now, let's go to longshore currents. I think it's on the next slide. Yeah. Now, a lot of times your swells are coming in this way, and the return is like this, and you have breaking over the top. Okay? That's sort of the classic. But what if you also have a tendency of water to move down the stream, down the beach like this? That's called the longshore current. It could be there's a river up here that's dumping in here, and that's feeding into the current. It could be just about anything that's having a current like that. At the same time, you have the waves coming in like this. That can create quite a situation. I don't do it much anymore, but when I was younger and we did go to the beach, I didn't go to the beach much when I was young, I liked to, what they call body surf, you know, and I would go out as far as I can and try to catch a wave coming in. And I did that repeatedly, and then I'd usually stop and get a little tired and look up and found out I didn't know anywhere where I was, because these longshore currents had dragged me down the beach. When I thought I was going back and forth, it was actually taking me down the beach, and occasionally I'd have to get out of the water and walk up a quarter of a mile, a half mile before I saw anything I recognized, because I had drifted with those longshore currents. The motion parallel to the shore, and this produces rip tides upon entering the channel. Okay? Now notice there the key word is channel. Obviously there is some sort of a deeper area, like where that river or stream or creek or something came in, and this produces what we call the rip tides. Now they show here rip currents moving that way. Rip tides are related to that, but that would be the tendency to have motion in two directions, basically. I'll just leave it like that. Okay? Now, this making sense? All right. Now, I said most of the time your waves are caused by wind. Occasionally they're not. Now, these are generally infrequently occurring phenomena, but when they occur, they are major. These are your tsunamis. The word tsunami actually comes from a Japanese word. I don't know exactly what it means, but I think it means big wave, okay, or something like that. These are ocean waves not created by wind, but by vibrations of the earth. In other words, earthquakes. These can be, and quite often are, the very largest of your ocean waves. Do they happen always? No. Do they happen frequently? Generally not. In fact, fairly rarely. But when you do have even small earthquakes, you can create quite a disturbance. Okay? So, what are some of the physical characteristics of those tsunamis? Catch this one. Speeds approaching 700 kilometers per hour. that would be 420 miles an hour. 420 miles an hour, that is moving. And especially when you're talking about huge volumes of water. Moving at that kind of speed, the energy is incredible. Now, wavelengths. Remember what the wavelength was? Crest to crest, 200 kilometers. That would be about 140 miles. 140 miles. That's the distance from here to Atlanta almost. Okay? Between one crest and the next crest. But moving at 700 miles per hour, kilometers per hour, which would be about 420 miles per hour, you can cover that in a very short time. Okay, very short time. Now the wave heights. Notice we've hit. This is related to the period, not exactly, but close to it. Wavelengths, and now wave heights up to half a meter. What's half a meter? About 1.5 feet, 18 inches. This is about 1 meter, so half of that would be about knee high. Okay. No big deal, huh? But that's in the deep ocean. So if you're out there on a ship and one of these passes you probably will notice it because 1.5 feet change is noticeable. But it can reach over 8 meters once it gets in the shallow water, because you have all this water coming in, and then you hit the shore, and you don't have the volume anymore, so it has to go up. Okay? Now, what's 8 meters? I'm about 2 meters. The ceiling's about 3 meters. Okay? It would be, if it's 3 meters on one floor, 2 floors would be 6 meters. You're between 2 and 3 story building. Wall of water coming into the shore. I don't want to be there. Most beach houses, 1 or 2 stories high. Swamp the whole thing. Okay? The big motels and stuff like this they put on the beaches, you go 2 or 3 stories on that, you're going to cause a lot of damage, a lot of flooding for 2 or 3 floors. Reach up over 8 meters in the shallower water. Okay? That's pretty tall. Now, with speeds like this, heights like this, wavelengths that big, you got to have a good warning system. You don't have a lot of time to deal with it. So when tsunamis are coming, and this is one of the most successful international cooperations they've ever had, the seismographs are one, and the tsunami warning system is the other. Every country that borders a sea or ocean has contributes to this, inputs into it, and they do great cooperation around the globe of the tsunami warning system. And boy, that has saved an awful lot of lives. Now, the most recent serious tsunami I heard about, and I think when Fukushima happened, there was a tsunami, but it basically went right into the island really quickly. That's Japan. It caused a lot of damage, flooded a lot of things, but it was pretty short range. Couldn't have much warning there. Okay? The more significant one I recall is when they had an earthquake off the coast of Thailand or Indonesia, somewhere here, and then the tsunami went across the Indian Ocean and slammed into the east coast of India. That did a considerable amount of damage. We had friends from Madras, which is also now called Chennai, real close to the beach. It's a beautiful, I think, Sunday morning when it happened. People were out there enjoying the beach, and with almost no warning, this huge wall of water came in, and it did kill quite a few people. But there was enough warning. People headed to Highlands and maybe got damaged a little bit, but nothing fewer deaths, and they just didn't have a lot of time for the warnings to sound. Okay, that's waves, tsunamis. By the way, there is another very good article. I really encourage you to read this one. The Health of Chesapeake Bay. Does anyone know where Chesapeake Bay is? Further south. Virginia. Okay. Chesapeake Bay is, south of Washington, D.C. Well, actually, I'll take that back. It includes Washington, D.C., and is a little bit north and probably somewhat south of that as well. And it's a pretty major area, shipbuilding and other things going on there. Been occupied quite a while, but it's not in the best of shape now. This blurb here tells you some of what's going on there. The Health of Chesapeake Bay, well worth a read. Okay? Then there's a smaller blurb on the next page of my book, 615, Rogue Waves. Generally a wave that just comes sort of out of nowhere and just does a lot of issues. That's worth a read too. It's not a very commonly occurring circumstance, but it can happen. There are a couple of examples there that give you some numbers to play around with waves as far as heights and speeds and things like this. But now we're moving. Now this is where I think the book and the slides are getting off a little bit. My book doesn't have much on the tides here. They had this back in the chapter on the moon. If you remember that, this is a reproduction of that. The tides are produced by Earth-Moon gravitational attractions already described back in chapter 16, I think it was. The basic pattern he produces with the tides, 2 high tides and 2 low tides every 24 hours and 50 minutes, okay? Not quite twice a day, almost twice a day. Most days twice a day, every now and then, like every couple of months, you'll have a day without either 2 high tides, well, maybe a little more frequently than that, without 2 high tides and 2 low tides in a day. You'll have 2 of one of the other every now and then. Now these can produce strong reversing tidal currents in very narrow bays. Okay? I think the worst of these that I remember reading about, I think is in Nova Scotia, and they have tides that go, I think they said 20 meters or something like that. That's enormous. Like I said, 3 meters is a story. 20 meters would be 6 to 7 story building tide twice a day. It's up and down like that. I can't even imagine. I may have my numbers wrong, but it's pretty amazing. Now, the tidal bore is a wave moving rapidly up a bay as the tide rises. And I can remember at least one mystery novel that I read, and the whole crux of it was, did this person get sent out there, in other words, someone killed them, but got away with it because they left them out there when this big rush of tidal bore was coming in, or did they commit suicide? Because in some places, this can be major. In fact, if you're out there in the water when this tidal bore comes, the odds are you're not going to be found. Not that you'll survive. You're not going to survive. You won't even be found because the water rushes in and the water rushes out, and you don't know where you're going to end up. Okay? That's a little gory, but that's... here's Darius. If I can find my pen. There it is. Find the grade book. There it is. And find Darius. There he is. All right. Anyone else come in since the called roll? We're slowly gathering. Just finishing on tides. Now we move to ocean currents. Okay? And that's where I was trying to find before in the book. This is around page 616 in my book, plus or minus there for you. Okay? Ocean currents. All right. When I say the word stream, what do you think of? Yeah.
Like a tiny little, almost a river, but not quite.
Okay. Something smaller than a river and probably a little bit larger than a creek or about like a creek, right?
Yeah.
Just a little flow of water somewhere. Well, when we're talking about ocean currents, streams, well, a stream on land transports water from a high elevation to a low elevation. That's what streams do. In the ocean, streams also transport water over large ocean distances along roughly the same path. When I mentioned the Gulf Stream, okay, lots of water moving long distances continuously. Okay? Why do these currents occur? Two effects. Not three this time, only two. One of these is density differences in seawater. Now, can anyone think of features that may change the density of seawater? Create some of these different densities. Say again? Okay, the salt will contribute a little bit for sure.
How many organisms it has?
How many what?
Organisms it has in it.
Okay, that might be a little bit, but that usually equilibrates out. The other big thing is temperature changes. You know, warmer fluid expands and cooler fluids contract. So you have contraction expansion going on because of temperature differences. So that's one effect. Different density differences in seawater, and it could be caused by salinity, and there's other things too. Fresh water coming in, like from a river or a stream or something like that, that changes salinity for sure, and could also change temperatures. So you have lots of things that could cause those density differences. The other thing, though, is winds blowing persistently in the same direction. The same type of concept that I was talking about with swells now have that wind constantly blowing at about the same rate for days on end. That is going to increase the possibility of a stream motion. Now, remember when we were talking about, remember the globe spins looking down from the top in a counterclockwise direction. The atmosphere over the globe doesn't necessarily move with the globe, with the Earth, because it's not attached. And basically the Earth spinning this way, the winds tend to be east to west near the equator. In the northern or southern hemisphere, in the middle latitude, they turn around and blow west to east. That's why our winds are prevailing westerlies. However, near the equator, those winds are almost always east to west, and generally blowing at fairly constant, regular speeds and directions. Okay? That's going to create pickup, the friction of the wind on the water is going to sort of move the water in one direction. Now, in the old days, in the sailing days, those were called your trade winds. Because if the sailing ships could ever get into those trade winds, just put up the sails and it took them off. Okay? It's when you got into north or south, you would get the dead zones when the winds were going easterly, then north of that they're going westerly, or south of it they're going westerly. In between you sort of have dead zones. Boy, if you were caught in some of those in a sailing ship and had no other means of transportation, you could be, they used to call it dead in the water for long periods of time. Okay. So anyway, that's the second effect. Winds blowing persistently in the same direction for long periods of time. So let's look first at the density currents. The denser water goes down, the less denser water rises. The denser water displaces less dense water in deeper basins. Three influences again. First I mentioned was water temperature. Now, picture this. Let's get in the Atlantic here. Okay. Polar water up here, say between Scandinavia and Greenland, very cold water. Colder temperatures, denser water, it sinks to the bottom. And the globe tends to be heading downhill that way anyway, and the sinking water moving that way, that creates a current. A pretty strong current there. The polar water is colder and denser. The water in the tropics is warmer and less dense, so you have this kind of motion going on. Polar water going deep and low, warmer water going up and north, okay? Water temperature creates some of those currents, density currents. Salinity has, why am I going blank on your name? Shelby. As Shelby said, salinity, salt accumulation, some mechanisms here, okay? When water freezes near the poles, okay, it's the water that freezes, not the salt. So the water freezes, it's pretty much pure water. Now that leaves more salt in the water underneath. So now not only is it cold, dense water, it's now salty, dense water. So it's really going down, okay? So the freezing water near the poles create a greater density for those cold waters. But you also have evaporation and runoff in warm pockets. So it's near the equator or the Mediterranean Sea. Now, the Mediterranean Sea, believe it or not, is not that far north. Okay? What would you say is equivalent to the Mediterranean Sea here in the U.S., latitude-wise? Say Kansas? Okay. Actually, you're not far off. It's just about the same as Washington, D.C., that area. Not as far south as we are, but further up. And yet we think of the Mediterranean as being warm, don't we? A couple reasons for that. It's almost completely surrounded by land. And land tends to warm up faster than water does, so it tends to be a little warmer because of that. Okay? But not just there. Near the equator, you have lots of evaporation. That evaporation then is going to increase salinity and make it a little bit denser. Okay? They mentioned the Mediterranean Sea, but there's more places than that. And then you are talking about the life in the sea, but think more of the deposits in the sea. Okay? Suspended sediments. And this could be where a river or stream or something is dumped into the ocean and really mixed up things, carry those along. That increases density. Of course, it's not salt water, so it's a little less dense because of salinity. But if you have a lot of sediments, that makes it more dense. But also, if you have shallow areas with lots of wind and stuff going on, you increase turbidity there too. So produce turbidity currents to the oceanic basins. So those are the three major influencers of density currents. Okay? Here's the illustration that shows that. As I said, they're talking about between Greenland and Iceland. I was saying between Greenland and Scandinavia, a little further north. But here, these cold waters here are denser than the warm water, and they head down the Atlantic, okay? Deep into the Atlantic. And look at this. They're showing Antarctic water coming from this direction. So you have cold currents, deep currents moving in directions like that, whereas your warmer, more surface-type currents, like the Gulf Stream, is coming up around like that. Now, not going as high as Greenland generally. Okay? So that's your temperature density currents. Let's look at your surface currents. We looked at density currents, now surface currents. The global circulation patterns maintained basically by patterns of prevailing winds. Remember we said that was the other thing. Your trade winds blow basically east to west. In the temperate areas you have prevailing westerlies. Now, not only by the wind, but also the rotation of the earth. Rotation of the earth is causing some of the wind, but it's also, with the earth spinning like this, the water kind of gets backed up. The soil has to move, the water is more fluid. I don't know if you realize it or not. You know what is in this little stretch of land right here? It's called an isthmus. What's that? Isthmus of what? There may be one. I'm talking about this. This is in Central America. Famous isthmus down there. Very thin strip of land between two oceans. Okay. I'm going to give you, this has nothing to do, well, not much to do with what we're doing. I'm going to give you, do y'all know what a palindrome is? Any of you? Yeah, it spells the same backwards and forward. Now, this is not to do too much with a surface current, but I'm going to give you the longest palindrome I've ever seen. I'm not saying it's the longest one I've ever seen. Well, let me get my pen. Okay. A man, a plan, a canal, Panama. Okay. You know who they're talking about? The man? Teddy Roosevelt. Teddy Roosevelt was the one who pushed through the building of the Panama Canal. That's the isthmus I was talking about. And if you see this, this is AMANAPLANACANALPANAMA. Backwards, a man, a plan, a canal, Panama. Spelled the same way backwards and forward, a palindrome. That's what I was trying to get at, the Panama Canal. Now, can any of you sort of describe or tell me what goes on in the Panama Canal? Is it just a split between the two oceans and ships drive through? What's that?
Yeah.
For trading, absolutely. It's a big deal. This is why Teddy Roosevelt did it. The seaports on the eastern U.S., those were the busiest. If they were trying to trade with the Far East, they either had to go around the world this way or down around South America, which is some of the roughest, nastiest, worst waters in the world, to get all the way back up here. Not a great thing. Added a lot of cost to our global trade. So he thought, let's cut a ditch through Panama, the thinnest part there, and then ships could go through there. Decreases big time the time of transit and other things. Let me get the roll updated here if I can find my pen somewhere here. I'm sorry? Okay, now what are you saying?
The test for the on the test.
Okay, a test?
Yeah, the test that you had gave Tuesday.
Okay, what about it?
Yeah, I ain't taking it. Can I take it?
Okay, why don't we take it at the end of the class when we'll be taking other tests?
Oh, okay.
Okay? All right. So here, Carl came in, and Terry came in. Okay. Does anyone else come in since the call roll? Okay. A progressive roll call here. All right. That's what I was getting at. But what my question was, and I've heard several good answers, but the question was, do ships just sail through the Panama Canal? Why not?
No, they've got like eight fills and then always the ship.
Absolutely. Okay? Remember, the Earth is spinning like this. So water piles up on the Atlantic side and drops off on this side. They have to go through several of these, I can't think of the word now. It's gates. Second. Sort of like levees, okay, very similar to that, to raise and lower. They go in locks. That's why they call them the locks. They go into one lock, and then they, say from the Atlantic side, close this off, open it up, the ship sinks down to another level, goes to that level, close this gate, open the next gate, and then sinks down again, and finally they get on the level of Pacific. I can't remember how many locks you go through, maybe 3 to go from the Atlantic to the Pacific. Of course, coming the other way, which ships do too, they come in here, close this gate, open this one, raise them up, go to the next lock, close this gate, open this one, raise up again. So it's a slow process, okay? And depending on how big the ship, there's not that many can be in the lock at the same time, okay? So it is things do get bottlenecked there. Now, not only there, another major canal, anyone know that one? In Africa? Can't find it. I see it, yeah, there it is. Suez Canal, exactly. I think actually built before Panama, and that's between the Arabian Sea, Red Sea, and the Mediterranean. But again, because of the spin of the Earth, the water piles up on the Red Sea side, and you have to go through. I don't know if it's as many locks there. It may only be 1 or 2 there, okay, to pass through on that side. Now, something pretty embarrassing. I can't remember the whole story of it, but one of the countries, I think it was Egypt, was celebrating a big anniversary of the opening of the Suez Canal, and they showed some pictures. The people who knew what they were looking at said, "Wait a minute, that's the Panama Canal." And suddenly they said, "Whoops, you were right." So they had to close down that part of the publicity because they were advertising not the right canal. And you would have thought they would have gotten that right, but they didn't. Anyway, that's what I'm saying. The surface currents are also influenced by the rotation of the Earth and the ocean basin shapes. Now, I don't know if you have thought about this. Where would you say some of the tallest mountain ranges in the world are? Asia? You're thinking the Himalayas? They certainly are. Those are not the tallest mountains in the world. Say again? Africa has a really tall mountain, Mount Kilimanjaro, because the distance from prevailing land to the top, that's even taller than Everest, but Everest is a higher elevation, but not even that. The tallest mountains in the world are in your oceans. If you remember an earlier slide showed how deep the average depth of the ocean was as opposed to the average height of land in the continental part. No comparison. Much deeper here. Some of those mountains make all the way to the surface to form islands. Those are the tallest mountains. It's just that they're way below water is the base of them. But they can be quite tall. So therefore the ocean basins say, don't even think that it's a nice flat area. It's not. There is terrain down there just like you would find on a continent. Now, they mention a term here, and I assume that's pronounced gyres. I've never heard it pronounced, but I think that's pronounced gyres. Great systems of water circulation centered in the mid-latitudes, and the direction is dictated by the Coriolis effect. So again, the middle latitudes, where you have the spinning of the globe like this, that's creating motion in the water, and periods in the ocean in the middle latitudes, both north and southern middle latitudes, then the Coriolis effect gives it that twisting motion. It's like, this is not probably the best comparison, but I think that's my phone. It may have something to do with our.
Oh yeah, there you go. I submitted mine last night. Yeah. No, I think Mr. West likes to do it. Yeah. English teacher too. I usually have, he likes a certain thing in the paper, like he looks for the same type of stuff, no matter what story you're reading. It's easy. I learned very quickly, okay, what are three ones in the story after working around many ones? And I usually get an A on this paper. I hope they don't count. See, I have the opposite problem. Usually when you Yeah, I can think
All right. I'm sorry, I was hoping that was the, oh, I forgot to turn off. Okay, it recorded everything Brandon was saying. No, Brandon was saying, no, I'm just kidding. I was hoping that was Channel 13. It wasn't. It was the Vice President Secretary, something about the trip tomorrow. Thank you. So, those are the gyres. They're great big circulation. What I was going to say, what a hurricane is with the air, great big circulation of air. A gyre is like that with the water. Not that powerful or strong, but it does happen, and that direction is dictated by the Coriolis effect. That would be a low pressure area. It would be counterclockwise up north, clockwise down south. High pressure area, clockwise up north, counterclockwise down south. Okay. So those are your gyres. Not a major thing, but some. All right, this is a figure from your text. Okay? Page 617, very busy figure. But get used to it. Your lab today on chapter 24, it's not all of it, but part of it's going to be right off of this. Okay? So catch this, know where it is, know how to use it. These are some of the currents, surface currents that we do have on the planet. Here's the one we're most familiar with, the Gulf Stream, which brings warm tropical water up along the eastern seaboard of the U.S., making as far north as New Jersey, Long Island, great beaches, even though they're pretty far north. Okay? Over here on the west coast, the California current goes southward, dragging cold water down here. San Diego way further south than New Jersey and Long Island are up here. Very cold in the middle of the summertime. The water, the land temperature is very pleasant, but the water temperature is quite cold. Most people, when they go to the beach out there, they're in wetsuits because it's just too cold. Here in New York and Long Island, New Jersey, bathing suits. No problem at all because of those surface currents. Here's a Labrador current coming down this way. That's what keeps a lot of Canada's ports frozen in the wintertime, that very cold frigid water coming down. The Gulf Stream continues over here, actually keeping Ireland and England, even though they're as far north as Nova Scotia, they stay ice-free. Nova Scotia freezes over because of the Labrador currents. Here's that polar currents coming down here, probably very deep currents. Here's the, I can't read all the names here, but North Equatorial current. Now, notice here, also, the equatorial, South Equatorial current goes this way, which you would expect because of the spinning of the Earth. The equatorial countercurrent, why is it going this way? And this one's going that way. Those are countercurrents. You would think they'd be going the opposite direction, but it's just because of the way, it's either the deepness of the current or something else is causing that. Okay? The countercurrent should be heading the other way. That's why they call them countercurrents. These are actual currents that are not counter. These you would expect to go this way. These you would expect to go this way. They're in the middle latitudes. Okay. But these in the tropics you would expect to be heading that way. All right. And here, this currently don't name it here, but this is what keeps Japan free of ice. And that's pretty far north. Now, some of these upper islands, they would get icy, but Tokyo, never. Okay. Over here in Korea, very, very cold. Here in Japan, same latitude, warmer because of the currents. So the ocean currents, the surface currents, greatly influence climate of different parts of the globe. All right, any questions on that? You'll see this again when you're doing your lab today. All right, now let's look at the ocean floor. Okay? Let me go and get this slide up. Okay. On the east coast of the U.S. and in other places like that, you typically have a very long, extended, what they call continental shelf. Okay? Here is the eastern coast of the U.S. This is continental structure here, but the continent continues even under the water, a long, gradual shelf down like this. Finally, you reach the continental slope that's there. The continental shelf is eroded continental margins. Why is it here? Over time, the sand, the silt, the clays, the soils, maybe bigger things, have eroded off the land here and filled in underneath the water. It's called continental shelf. Finally, when you reach the edge of that, the steeper transition feature is called the continental slope, okay, beyond the continental shelf, often cut up by submarine canyons. These are not nice, smooth little things like this. You will actually find, like the Grand Canyon, maybe even grander, great big cuts and gouges in that shelf, slope, continental slope, okay? Now, the ocean basin is in sort of the relatively flat part. Don't think it all this flat, okay? It has mountain ranges and other things in it, but in general, it's fairly flat. The ocean basin, deepest part of the ocean, that's not really the deepest part, but the deepest flat part of the ocean, characterized by practically level abyssal plain, that's what they call this, fairly close to level, but also mountainous ridges. Here's a mountainous ridge, there's some seamounts here. So you'll have these all broken up, but the relatively flat parts would be the abyssal plain. That's part of the ocean basin, as well as some of those low mountains and ridges and things that are in there. Now, okay, the ocean basin contains these trenches. Those are the deepest part. Now, why is a trench over here and a shelf over here? Any reason? The plate tectonics. This is probably all part of the same plate. So it just is pretty gradual here. This is oceanic plate subducting under a continental plate, and you have a big trench here. You have this on the western U.S., you have it on the western Atlantic, or eastern Atlantic, you have the trenches. In the east coast of the Atlantic, you have shelves. Now, sure, there's a shelf here, but look, this shelf is nice and long and broad. This is, I mean, this thing is that big. It's just very, very gradual. The slope hits you almost immediately. And on the west coast, you go out of San Francisco Bay, you watch your depth finder, and it's going on, boom. I mean, it just drops off immediately. You do that on the east coast, and finally it drops off at the continental slope. Much more gradual on the eastern coast of the U.S., big old trench on the western. Okay. Then there's also volcanic peaks on scattered seamounts. Some of these are underneath the ocean. Some are mid-Atlantic range or ridge or something like that, like we talked about in the Atlantic, Rift Valley in between. Or the Hawaiian Islands, these seamounts have actually crested the surface. And those are not between major plates, but weaknesses within a plate that created the Ark Islands there. Does that make sense? Okay, before we do too much further, I missed this one. People behind the science, Rachel Louise Carson, a U.S. biologist, conservationist, and campaigner. She, well worth a read here. If you choose to write on her, this can't be your source. This may be the source of the idea, but you have to find your source outside the book. Remember that. Remember, 10 of you have not turned in papers. Only 5 of you have. Okay? Now, let me also say this, because several people have come in since I made the announcement earlier. It's on Screencast-O-Matic. It will be on YouTube, but it'll be a while before I get that uploaded. And that's this. I still don't know if and when we're going to make it to Channel 13. I called them and talked with Harmony Mendoza, I guess that was Tuesday. She said she would send an email outlining, everything to me. As of yesterday, I still had not received the email. She's acted like she's going to do it right away. She either got my address wrong or didn't get it done. I don't know. So I called Jerry Tracy yesterday, went straight to his voicemail. So far, I haven't heard back. Then today, I called Miss Mendoza 2 more times, once when I got out of my previous class, and then right before I came to this class. That's why I thought that phone call was maybe them calling back. Never got an answer. I left a message again on voicemail, and the second time I just hung up because I'd already said everything I could. So anyway, how I got off onto that, your papers are due next Tuesday. Thursday is the final exam. Tuesday is your last day you can turn in your papers without losing points. Get up in Tuesday. That's the February's over with Monday. So if I don't have them by Monday, then you don't have any bonus points. If I get them after Tuesday, you start losing points. Okay. So please get those in. Now, say again? I can't hear. Okay, great. All right. Now, yes. Say that again. You can, but let me warn you this, okay? I receive emails, I don't mind, but I have received some papers by email that the formats were just totally screwed up. Now, I don't know if that's how they were sent or if they got butchered in the email system, but I have to grade what I receive. So I'll leave it up to you. If you want to know what you're turning in to me, print it out and you say, yep, that's what he's going to get. If you email it to me, I grade what I get. I print it out and then I grade it. Most of them come across fine. It's only been in rare occasions, but they come across really squirrely. I'm guessing they sent them to me squirrely. They didn't notice that the format was screwed up or something happened. I don't know which, but I have to grade what I receive. So it's up to you, okay? If you have a screwy format, you're probably going to lose a few points, okay? So, but most of the time, there's no problem. Okay, but I do want to warn you of that. So, while I was saying all this, if we don't get to go to Channel 13 on Tuesday, then we're going to have an additional lab on Tuesday. And that lab will be your presenting your papers. Okay? And I'll give everybody between 5 and 15 minutes. I'll let you choose how long you want to present. But you'll be presenting your papers Tuesday. If we get to go to Channel 13, then we won't have time for that. Okay. So, you got to get your paper. And if you've already turned in the paper, I'll give it to you back so you can prepare your presentation. But you'll need to turn that back in at the end. Yes?
On Tuesday, if we don't go to the weather channel and we do the presentation, if we get done with the presentation early, are we taking our exam Tuesday or just still doing it?
Okay, we're going to have the test on Chapter 24 Tuesday.
Okay.
Yeah, and then the exam, the final comprehensive exam will be Thursday. And frankly, that's going to be very short, okay? It's going to be pretty easy and you'll be out of here in no time. Which also leads me okay, there is a chance we'll be going to, if we can't go to Channel 13 on Tuesday and we do presentations here, they may still say, but you can come Thursday. Then we'll go there and then come back, take the final and be done, okay? So I'm hoping we'll get to go one of the 2 days. If we go Tuesday, there's no presentations required. If we go Thursday, then we'll still do the presentations on Tuesday and do the trip and the final on Thursday. Because we've got plenty of time. He's not going to keep us there more than 2 hours, I don't think. Yeah.
If we have presentation on Tuesday and go on Thursday, would it be extra credit Thursday if we go, or
Okay. As in all of the both field trips. They're optional labs. You get 25 points if you go. You don't get anything if you don't. Then at the end, I do drop one lab score. If you go to one field trip, you get to drop a second one. The 25 can replace your next lowest lab. If you go to both of them, you get to do that other. If we do presentations, you get to drop yet another one. If you do your presentations, you get 25 points. If you don't, you don't. Okay. Optional in the sense you're not going to get your 25 points if you don't give, but if you don't have to give, but I would prefer, that's going to be part of class, is to do the presentation. So be prepared to at least tell what you've written about, give a quick description. Try to keep it 5 to 15 minutes. 5 will go by pretty quickly. 15 will get a little old, but if you got interested, go for it. Okay? That's why I took the break here to say that. All right. Here are some other features of the ocean floor. These are your ridges, okay? Your trenches and your ridges. The trenches are the dark areas, and the ridges are the light blue, okay? Ridges are rises, trenches are depressions. And as you'll notice, major, and you'll see this again, this is going to be part of the lab today. Here is the deepest point in the ocean, the Marianas Trench. I can't tell which one of those is Marianas. Goodness, this is so dark. Yeah, the Marianas is, yeah, I thought that was it. This is Marianas, this is Mindanao. Okay, so that's the deepest part of the ocean right there. So the dark blue are your trenches, the light blue are your ridges. Okay? Which it seems like we should have had that a while back. Okay. Any questions? That is it for chapter 24. That is it for the course. Okay, as far as what new material we're going to cover. Let me just quickly go over where we are now. Let me do my standard blurb that I always do. Okay. The summary here at the end of, okay, you know what comes first. Nothing replaces reading the chapter, okay? Please read the chapter at least once more, maybe twice more before your test. That'll be Tuesday, okay? The summary here is about average length, maybe a little short of average, has quite a few high points in it, but it doesn't cover everything. Key terms, maybe about normal or a few fewer than normal. Presented alphabetically, but they give the page numbers where the terms first were defined or described. Then applying the concepts, 46 questions about average, multiple choice. I think the best thing to study for the test, the multiple choice questions. But then there's also questions for thought, 13 questions for thought. Maybe not quite average, but close to it. For further analysis, 6. That may be a few more than average. There's an invitation to inquiry on water use that you can think about that if you'd like, and you can probably get some of the data and put that together. That could be a paper topic. And then there's parallel exercises. We didn't do many of these as we went, but if you do have the big book, the answers to the Group A are in the back, Group B are not. If you have the thin books, none of the answers are in the back. All right. So where do we go from here? The time is now 2:30. Okay? We can start fairly soon for the lab on chapter 24. Okay? I don't think it'll take you a full 2 hours, but you have as much time as you need. And then when we finish that, and this, I mean, it's working out just about perfectly. 2:30 to 4:30 would be what would be allowed, and 4:30 to 5 would be the test on chapter 23, which we finished last time. So this is ending, I couldn't have planned it this way, okay? It's ending just about perfectly for that. What will we do Tuesday? Hopefully we go to the Weather Center. If we don't go to the Weather Center, y'all are presenting your papers. If we do go, we will meet here at 12:30, and that will be a time you can turn in late work, make up late tests, make up late labs until we have to leave to go. And I will also be returning papers to you. All your labs, all your tests, and everything. So anything you don't have made up by Tuesday, you're going to get 0 or very poor grade if you just turn in a little bit. Remember the Moon Lab? We did most of that in class. So don't fail, okay? This is Coco, right? Hi, Tanisha. Okay, I couldn't tell from here. Okay, Tanisha. All right. Of course, right when I finish saying all that, someone new walks in, so let me say it again. Sorry, y'all have to hear it again. We just finished chapter 24. What we're about to have is a lab on chapter 24. Okay? It's all going to be from the book. They're not going anywhere. We may go across the hall to the other classroom, but there's no outside material. All of it's from the book. Okay? After you finish the lab, we'll have the test on chapter 23. We finished chapter 23 last time. We'll have the test on 23. After you finish the test, you can head home. Okay? Now, Tuesday, last day of class. Okay? It's the last day to get any tests made up, any labs turned in, and that type of thing. We're hoping, and that includes getting your paper turned in without losing points. We're hoping we're going to be able to go to Channel 13 Weather Center on Tuesday. I still haven't heard from them. I'll try calling again. The trouble is I'm going to be out of town all day tomorrow, so I won't be able to call any then. So hopefully I'll know something by Monday, okay, whether we go to 13 or not. If we don't go to Channel 13 on Tuesday, that means you get one more lab, and that lab is going to be presenting your papers. Okay, 5 of you have turned them in already. You can get them back if you want to, so you can practice and get together your presentation. If you don't, haven't turned in the paper, you got to write your paper and get ready to prepare it on Tuesday if we don't go to Channel 13. Okay, also on Tuesday, the last 30 minutes that we're here, whenever that is, we'll have the test on chapter 24, the chapter we just finished today and that we're going to do the lab today. Then on Thursday, I'll be returning any other work that you turned in on Tuesday I didn't have a chance to grade then, and answer any questions you may have. And by the way, I forgot this one. Your student course evaluations for first mini-term courses are now open. Okay? Any of you done that yet? 1, 2. The rest of you, please get those done before Thursday. Okay, if possible. Otherwise, I'm going to ask you when you do the thing and say, please get it done. Because it's so easy to say, oh yeah, I'll do it tomorrow, and then you're through with that first mini-term, you forget to ever go back and do it. Okay, question?
We get bonus points for turning on paper and 20 of February, right?
Yes, by Monday. If you turn it in today, tomorrow, or Monday, you get your 1 bonus point. If you turn it in Tuesday, you get 0 bonus points. If you turn it in Wednesday or afterward, you get minus points. Okay, negative bonus points. Yes.
Do you want us to print it out and bring it here, or do you want us to turn it online?
Okay, I answered that question a little bit earlier. I will accept email papers, but I have received some before, not many, not most, just a few. I have received some before that came across the formats were just totally squirrely. I have to grade what I receive. So if you want to make sure I'm looking at the same thing you're looking at, I would say turn it in. But if you want to try to do the email, it should come across fine. I don't know if those squirrely ones were squirrely when they sent them or got mixed up in the transmission. I don't know. But I had to grade what I had. So I will accept it either way. Okay? Any other questions? And then Thursday will be returning everything else. And since Thursday's going to be such a light day, y'all want to just have pizza? Okay. Anyone have any dietary restrictions? Thursday. We'll talk about it Tuesday. We'll have plenty of time to talk about it. Be thinking about it, and I'll run over and pick up pizza at probably Little Caesars. It's close. And so think about that for Tuesday. Okay? We're going to have it on Thursday, but we do. So we'll have pizza. I'll return all other papers to you, and then we will have the final exam. And then, sayonara. Okay. Get over it. Okay. Any questions? All right. Y'all ready for the lab, or you need to take a little break first? I don't hear anything, so I assume you're ready for the lab. Okay? That means these are due next Tuesday. Most of the time you have a week to do the lab. This one you have a weekend to do the lab. You can do them all today. But for people who are not here, no, I haven't. Is that something that happened because of it?
Yeah, it's a giant piece of radioactive waste.
Oh, wow. Sounds really good, yeah. I was looking forward to reading. What's that? All right. Let's talk about the lab for a moment. And if you need to go, first question, right out of a figure in the book. I showed it on the slide. Okay? Second question. I remember this was on the slide too. The first part, the three oceans, and there are only three oceans, but I say list two continents that border each of the oceans. So those are continents, not countries. Y'all know the difference in a continent and a country? Okay. If not, ask me before you put something down. I'll tell you whether it's a country or a continent. Then name 8 major seas, and I think you'll see these in a figure in the text, and name at least one country that borders each of those seas. Okay? Then, and this is the one I was just referring to, and by the way, the lab is written front and back. On the front, name 10 of the ocean currents and list an ocean in which each one is associated. Okay? So there's room there for 10. 5 on the front side and 5 on the back, and the ocean in which that current is located, is found. And you may have a current that goes through 2 oceans. Pick either ocean. Then name 4 of the larger ridges on the Earth's ocean floor and the ocean with which that is associated. Thank you. Okay. So that was one of the last slides we showed. And I said you're going to see this again. And then number 6, name 12 of the larger trenches in the ocean's floor and the ocean with which each is associated. That was on that same slide. Pick out 10 of those trenches and list the ocean in which that trench is located. Okay? Pretty straightforward. And just about everything is in the book, pretty much in a figure, though there may be some just in the words. And y'all can work together. You don't have to be Lone Rangers. You can work together, but turn in what you got. Yeah. All right. Now, I'm going to pause Screencast-O-Matic for now. If you have any questions, I'll try to remember to